Hi, I'm Ryan with High Desert Math Tutor, and today I'm going to take a few minutes to show you how to work through problems that focus on properties of integration. So there are two properties of integration we're going to need for these problems right here, and these are very common problems or types of problems that you would see when you're just starting out with integration. So to quickly review the properties you must know to answer this question, one, if we have a function that we're integrating and this function is being multiplied by a constant number, so note that c is a constant. So c could be like the number 5, could be the number -18, it could be a fraction. Well, if you're multiplying a function by a constant number and you're integrating that whole thing, you could actually factor that constant out and just kind of set it to the side, integrate the function, which is likely going to have smaller numbers now, and after you get an answer, multiply that answer from the integration by the constant. So this is one very common rule that we make use of for integration. Another rule that you will use quite a bit but not think about it too carefully most of the time, if you have a function that you're integrating that could consist in reality of two or more smaller functions being added or subtracted, you can take this one integral with these smaller functions and split this integral into multiple integrals that have the same limits of integration for each of them, but then we can deal with only integrating this function separately and then this function separately from each other. So finding the antiderivative of each of these would theoretically be much easier if you could just isolate one piece and focus on that and then get on to the rest. So now on to this question. So the problem we're working through today, suppose we have information about the function f. We know that the integral of f from 5 to 8 is equal to 5. We don't know what f is, but we know that the area under f, between f and the x-axis, between x equals 5 and x equals 8, that area is equal to 5. We also know if we take the integral of f from x equals 5 to x equals 6, that the area is equal to 6. And finally, still working with f, we still don't know explicitly what f is. But with f, if we integrate only from 7 to 8, the area is equal to 4. So with these 3 bits of information, we want to try to understand this integral a little bit better. So there actually is one more integration rule I haven't mentioned, which I will throw up right over here. And what this rule is if you have one integral going from a to b of a function, you can split up this interval a to b into multiple integrals. So let's say we have this picture right here. Now I'm going to ultimately erase this, so pay attention while it's here. So if we have a curve that goes like this, this is f of x. If we say the x value for right here, this is a, and over here, this is b, we could split this range up into c, d, e, as many pieces as we want. So for now, I'm just going to split it up into, say, one set with 2 different portions. So we'll go from a to d and from d to b. So here, we can take this one integral of f of x dx and go from a only to d. So we're only going to find the area right here. Well then, if separately we want to find this area from d to b, we can do that, and we can ultimately add this area right here and this one, both of them together, if we add the areas between the curve and the x-axis for both of these integrals, it's the same as just taking the area simply from A all the way to B, this whole thing. So you can take one large area that you want to analyze, and if it's easier, or the information to get the area is more convenient in smaller pieces, you can take smaller integrals and piece them together, either add them together or subtract them from each other to split this large region into smaller pieces. So this is the third rule that we really need to know for this problem, but I need the space, so if you need to look at that graph again, feel free to just pause or back up the video, rewind. Okay, so now, right here, to jump into the first problem we have for today, we want to find the integral of f of x from x equals 6 to x equals 7. But let's look at the information we have so far. We can go from 5 to 8, we can go from 5 to 6, and we can go from 7 to 8. So there's no explicit, clear information about f of x only between 6 and 7. But what we can do is start with a larger area, say all the way from x equals 5 to x equals 8, and we can cut away the pieces we don't need. So here, we'll start with a larger area from x equals 5 to x equals 8 with f of x dx. And let's take away, now I'll draw a picture for this to hopefully clarify. So let's say we have 5, 6, 7, 8. So we don't know what f of x is actually doing, but we can say, if we take a similar picture as what I had before, similar graph, between 5 and 8, which is what this integral represents as this entire area, we could take this integral, which represents the area between x equals 5 and x equals 6, and we can cut that off where we don't need that, because we really only care about right here from x equals 6 to x equals 7. So the way that we get rid of this extra area right here is by subtracting the integral that gives us that area. So the integral from 5 to 6 of f of x dx. But now notice, we have not just 6 to 7 like what we want, we have 6 to 8 left over. So if we can find a way to get rid of this extra bit of space right here that we don't want, then we would have left over only the piece that we care about. So right here, this integral goes from 7 to 8, which is what we want to get rid of. So if we subtract that integral also, what's left over should be all we really care about. So the larger area is equal to 5 right here, minus the area from x equals 5 to x equals 6 is 6, minus the area from x equals 7 to x equals 8 is 4. So if we combine these negatives first, we see we get negative 10, and then 5 minus 10 is negative 5. So this drawing, like I said, is not an accurate depiction of what f of x is, because we don't really know what f is. Now, in a general sense, we think of integration as the area between the function that we're dealing with and the x-axis. And it seems reasonable to look at all three pieces of this function that we have information on and to call each of those area. But we see now, if we take this first function and we subtract those pieces that we did not need, our final answer is actually negative, which is totally fine. But technically speaking, we can't call that area, because area is never negative. But for a practical sense, just so we can just talk and get through, it's pretty common to imagine this as area, but just area that's below the x-axis. So this would be the answer for the first problem. Now, moving on to the second problem, we're going to need to make use of some more of these properties. So backing up to clarify, for problem A, what we needed to make use of was this property where one large region under a curve can be split into smaller pieces that are added together, where if we didn't want one of these pieces, we could subtract that and get rid of it. Now here, for this next problem, the integral from x equals 6 to x equals 7 of 5 times f of x minus 6, we have multiple things being combined right now with subtraction. So often how we start problems like this is we take this single integral and we'd split it into two integrals, where we're subtracting inside, so we're going to subtract these two integrals from each other on the outside. Next, we can make use of another property where we're multiplying this function by a constant number. We can take that constant number and move it outside of the integral, where we can multiply the final answer by 5. Okay, now this is very convenient because the integral from 6 to 7, it's not one of these options here. We don't have those limits together on an integral, but this integral of f of x from x equals 6 to x equals 7 was our first problem. And we know that this integral is equal to -5, so we can replace the integral with -5. So this is ready to be simplified and we're done with that piece. But over here, this is a definite integral where we don't see any variables, but that doesn't mean we can't integrate this, because if we only have a 6, the antiderivative of 6 would be 6x, and the limits of integration would be 7 and 6. So continuing on, 5 times -5 is -25, and here we get 6, put these in brackets, 6 times 7 minus 6 times 6. And I'm going to show you a trick. I could have factored out this constant and moved it in front of the integral earlier on, like we did here. But since I didn't do that before, notice both terms inside these brackets have a factor of 6. So I'm going to actually factor out that factor of 6, and all that's left is 7 minus 6. And 7 minus 6 is 1. Then 6 times 1 is 6. And -25 minus 6 is -31. So there we have it. The integral from x equals 6 to 7 of 5 times f of x minus 6 can be split up to two separate integrals. One integral that relies on f of x, the other integral that doesn't rely on f of x, so we could just act like this doesn't exist and go back to the fundamentals of definite integrals, where we realize the antiderivative of a constant just brings you a single variable. And moving from there forward, we see that the final answer for this is -31, which again is not technically an area because area is never negative, but you can think of this as the area below the x-axis, which is why it's negative. Well, that's it. So these properties of integration anytime you see problems like this where they give you multiple integrals with a function, but they don't tell you what that function is, typically you start problems like this by rewriting the question integral, the integral in question. You rewrite this integral using properties of integration, and that's how you make use of this information that's been given to you.